In the last couple of videos, we looked at the symmetric group on n letters. We saw how to represent permutations, which are elements of Sn, as cycles, and we learned that any permutation can be written as a product of disjoint cycles. And we also saw that any permutation can be written as a product of transpositions, which may not be disjoint. We saw that a cycle of length k has order k, and if you have a product of disjoint cycles, the order of the product is simply the LCM of the individual orders. So these are the various things that we have done in the last few videos. I want to now spend more time on writing a permutation as a product of transpositions. So if you recall, one of the examples from the previous video, we wrote the permutation 1 2 1 3 1 4, and we saw that this is same as 2 3 2 5 1 2 4 5 and 1 5. Okay, so this is the same permutation, but on the left hand side we have a product description which requires 3 transpositions. On the right side we have 5 transpositions. Okay, I remarked on this last time. The description as a product of transpositions is not unique, and even the number of transpositions that is required is also not unique. We have 3 here, we have 5 here. However, what is unique is whether we need an odd number of permutations or transpositions or even number of transpositions. So this is one of the examples we saw. Another example we saw was, if you take the 3 cycle 1 3 2, this can be written as 1 2 1 3. This can also be written as 1 3 3 2. Okay, so here we need 2 transpositions. In this also we need 2 transpositions. So both even. Of course, in this case it's both 2. In this case these are both odd, even though it's 3 and 5. So the theorem that I want to prove in this video, and it will take me some time to prove this, we will do various examples to understand the proof, and then I'll prove. The theorem is, informally, if you want to say the theorem, it says that if a permutation as a description is a product of transpositions in 2 different ways, the number of permutations, number of transpositions required in both the things have same parity. So they're both even or they're both odd. So let me write this more precisely mathematically. How do we write this? Let me write it like as follows. Let rho be a permutation. So I'm going to use a new Greek letter because I'm going to use tau and sigma to denote transpositions. So rho, you read this as rho, RHO rho. Okay, so let this be any permutation. Suppose it has 2 representations. So suppose that rho is, on the one hand it is sigma 1 sigma 2 dot sigma k. On the other hand it is also same as tau 1 tau 2 tau t. Okay, where these are all transpositions. Sigma 1 through sigma k and tau 1 through tau t are 2 cycles. Remember, transpositions are just another name for 2 cycles. So what is the situation? We have a fixed permutation rho, and we have written as one fashion sigma 1 through sigma k, another fashion as tau 1 through tau t. Certainly we can't say k equals t, but what we can say is that then both k and tau, t, k is the number of sigmas, tau is the number of taus. Okay, so let me remove the word b both here. So then k and t are both even or both odd. So in other words, what I am saying is that one can't be even, the other odd, or that's not possible. Either both are even or both are odd, as illustrated in this example. Here you have 3 and 5, both are odd. 2 and 2 both are odd. Okay, so you can have both odd or both even. So the rest of the video is focused on proving this theorem. It will take some setup. So I'm going to slowly introduce to you the techniques involved. So this is not so easy to prove, though it would be, as we proceed with the proof, you will hopefully follow the proof and it makes sense to you, but the proof is somewhat lengthy. So let us systematically prove this. The goal of this video is to prove this theorem. Okay, so I will systematically and slowly go through the proof. So in order to prove this, let us introduce a polynomial. So let us introduce a polynomial. Okay, so if you are not very familiar with the notion of polynomials, don't worry about it. We don't need a lot about them. It is just a formal thing, and I will do enough examples to make it clear. So I'm going to call this polynomial f, x1 up to xn. So think of x1 through xn as variables, or indeterminates. So think of them as just meaningless symbols. Okay, they don't have any meaning, they are just symbols. So I define this to be the following. So I'll start with x1. I'll subtract from it x2. Then I'll subtract from it x3. x1 minus x2, x1 minus x3. I will do it all the way up to xn. Okay. So x1 minus the rest one by one. Then I'll start with x2. Okay. And I'll x2 to the right of x2 there is x3. So I'll start with x3. x2 minus. Okay. So if to basically what we have is x2 minus x3, x2 minus x4, and up to x2 minus xn all the way, and I finally have xn minus 1 minus xn. Okay, so this is the polynomial, and formally if you write compactly, if you want to write this is written like this. We take disjoint product. This symbol stands for product. You are all familiar with the summation sign. This is just the product sign. We take I and j distinct, I less than j. I can be anything from 1 to n minus 1, and j can be anything from 2 to n. Right? I can't be n because if I is n, there will be no j. J must be strictly more than n, I. Similarly, j cannot be 2 because j must be strictly more than 1. So this is the product. So for any pair of indices where I is less than j, you introduce a term xi minus xj. Okay. So and remember, n is fixed in the theorem. We are working with the symmetric group on n letters. N is any positive integer. We don't want to work with a specific one. The theorem works with any positive integer. But as an example, what would be x1, x2? Say f of x1 is just that doesn't exist. You don't have two indices like that if you have n equal to 1. So f of x1, x2 would be simply x1 minus x2. There is just one pair of indices, 1 and 2. What would be f of x1, x2, x3? x1, x2, x3 would be, you take x1 minus x2, x1 minus x3. So starting with x1, you take every other index. 1 is fixed, so 2 and 3. And then starting with x2, you take every other index. And then is there anything else? No. So here you have three possible. Here you have I equal to 1, j equal to 2 were the only possibilities. Here you have I equal to 1, in this case j equal to 2 or 3. When I equal to 2, you have j equal to 3. Okay, these are the three possibilities. So there will be three terms in the product. So this is x1 minus x2 times x1 minus x3 times x2 minus x3. Similarly, I will write one more, and hopefully it will become clear to you what is the polynomial it's an expression. Think of it as an expression involving variables x1, x2, xn. So here for I equal to 1, you have for I equal to 1 you have j equal to 2, 3 or 4, right? So for I equal to 1 you have j equal to 2, 3 or 4. So you have x1 minus x2, x1 minus x3, x1 minus x4. Okay, so what about j equal to I equal to 2? So you have I equal to 2, j must be bigger than 2, so j is 3 or 4. So you have x2 minus x3, x2 minus x4, and then I equal to 3, then j must be 4. So you have x3 minus x4, right? So these are the 6 terms. So this polynomial for x1, x2, x3, x4 will be these 6 terms, and so on. Now you can think of what x1, x2, f of x1, x2, x3, x4, x5 would be. It will be x1 minus x2, x1 minus x3, x1 minus x4, x1 minus x5, and so on. So this is what f is. Now what I want to do is, I want to take an element sigma in Sn. Okay, so sigma is just a permutation on n letters, and I want to define sigma star of f as follows. So sigma star of f will be, so f is, remember this, sometimes I don't write the variables. So we have, f is the product xi minus xj, 1 less than or equal to I, and I is strictly less than j, and j is less than or equal to n. So sigma star f I will define. So I'm going to modify f. So sigma star f is a modification. I'm going to change f a little bit of f using sigma. Okay, so think of it like this. Sigma star f is simply a modification using sigma. How do we modify? Remember what is sigma? Sigma just is a permutation of the letters. So what I'll do is, I will continue to take the product over a pair I comma j, I strictly less than j, but instead of xi minus xj, I will have x of sigma I minus x of sigma j. Okay, this might seem somewhat mysterious, but it is not. So I just want to make it very clear to you, because it's important to understand what sigma star f is before we proceed. So what is sigma star f? I'm going to start with f and modify the indices based on sigma. So as an example, okay, so let's suppose that f of, we take 2 variables. So then, so take n equal to 2. So then f is simply x1 minus x2. So if you take, now we are dealing with s2, right? So n is 2. S2 is just 2 elements, e and 1, 2. This we have seen. The order of S2 is 2 factorial, right? And which is 2. So it's e and 1, 2. So if you take for any sigma, we can define, so let's compute this in these 2 cases. E star f is, this is a compact way of writing x sigma I minus x sigma j, but if you spread it out, what would it be? E is identity element, so nothing changes. So you have x e of 1 minus x e of 2, but e of 1 is 1, e of 2 is 2. So this is just x1 minus x2, which is just f, right? On the other hand, what is 1 2 star f? So this is x Okay, so it's confused. Now it's easier for me to just use the letter sigma. So then this is x sigma of 1 minus x sigma of 2. See, when I write sigma of I, remember sigma is a function from 1 through n to 1 through n. So sigma of I is simply the image of I, okay, under sigma. So when I write sigma of I, I am actually thinking of sigma as a function. So what is the image of 1 under sigma, which is 1, 2? It is 2. So it is x2 minus x sigma 2 will be x1. So this is not same as f, right? This is actually minus f. So here we have changed the sign. x1 minus x2 becomes x2 minus x1. So this is what happens when n equal to 2. Let's do n equal to 3. Okay, so here what is f? Here f is x1 minus x2, x1 minus x3, x2 minus x3. Okay, and here s3, remember, has 6 elements. So they are e 1 2, 1 3, 2 3, 1 2 3, 1 3 2. Okay, let me do not all of them, but to illustrate the point, let me do sigma equals 1 3, for example. What is sigma star f? So you start with f and you keep the order, but you just change the subscripts and see what happens. So it would become x sigma 1 minus x sigma 2. So I am looking at f here, x1 minus x2, that becomes this. x1 minus x3 becomes x sigma 1 minus x sigma 3. And finally you have x sigma 2 minus x sigma 3. Benjamin, so I actually touched this, but it's okay, it's working.
I take the audio from you only, sir.
Okay. So you cut this.
Yeah, sure.
So sigma star f is x sigma 1 minus x sigma 2 times x sigma 1 minus x sigma 3 times x sigma 2 minus x sigma 3. But now let's actually compute these things. X sigma 1, remember, is sigma is 1 3. So this is x3. Sigma 2, what does sigma do to 2? Nothing. So it is 2 is fixed by sigma. So it's x3 minus x2. Sigma 1 is 3. So this is x3 minus sigma 3 is 1. So this is x1. Sigma 2 is 2. So this is x2 minus sigma 3 is 1. So this is x1. So sigma star is x3 minus x2, x3 minus x1, x2 minus x1. And what is this? This is, how do you compare this with f? So every term, remember, here is switched. x1 minus x2 became x2 minus x1. x1 minus x3 became x3 minus x1. x2 minus x3, you have x3 minus x2. So you have minus, minus, minus. So this is minus f. Is that clear? Sigma f is minus f because sigma f is a product of 3 terms. Sigma star f became, those 3 terms are interchanged. The order in which we take the 2 terms in x1 minus x2 is interchanged, so that becomes minus. So this is minus f because this is minus. Okay, so so this is minus x2 minus x3 minus x1 minus x3. This is minus x1 minus x2, right? And so this is minus f. Minus 1 times minus 1 times minus 1 is minus 1, and then you have just f. So sigma star f is f. Let's do one more example. Let's say tau equals 1 2 3. That's another element of S3. So tau is 1 2 3. So what is tau star f? Same thing. So f is the same process. It will be different than, the answer will be different, but the same procedure we must follow. F is x1 minus x2, x1 minus x3, x2 minus x3. So tau star f will be x of tau 1 minus x of tau 2, x of tau 1 minus x of tau 3, x of tau 2 minus x of tau 3, right? So this should be tau 1 is 2, tau 2 is 3. So x2 minus x3. Tau 1 is 2, tau 3 is 1. So this is x2 minus x1. Tau 2 is 3 and tau 3 is 1. Okay, so this is x3 minus x1. So now how do you compare this with f? F has 3 terms again. Remember that f has 3 terms. x1 minus x2, x1 minus x3, x2 minus x3. Here we have those 3 terms, but unlike in the previous example, one of those terms has not changed. x2 minus x3 remains x2 minus x3, but the other two things we have interchanged. This and this have changed signs. Right? Because it was x1 minus x2 in f, that has become x2 minus x1. It was x1 minus x3 in f, that has become x3 minus x1. x2 minus x3 remains as it is. So this is actually just f, because this is minus of that term times minus of that term. So minus 1 times minus 1 is 1. So tau star f is f. Okay. So what I want to now say is that, and I hope you agree based on these examples. So now if now I am going back to the general situation. If sigma is a permutation in Sn, then sigma star of f is either f or minus f. Okay, that's what we found in these examples, right? It becomes either f or minus f. Of course, doing examples is not a proof of this. The examples are supposed to give you an idea of why it must be true and how to prove it. And what is a proof? So I won't write this in detail, because it's easier if you think about it yourself and try to write down a proof. But I will give you a basic reason why this must be true. Because remember, f was product xi minus xj. Okay, so it is over all ij. And sigma star f is the product x sigma I minus x sigma j over the same I and j. So if you think about it, because sigma is a permutation, sigma is a bijection, right? Remember, symmetric group is the set of bijection of this set. Because it's a bijection, as I varies over 1 to n or 1 to n minus 1 in this case, sigma I also varies. Similarly, sigma j also is an element of 1 to n. So if you take an individual term in f that is translated to some other term, only changes will be negative signs, as we have seen in this example. For example, x3 minus x1, x1 minus x3 became x3 minus x2. So we must allow that in the definition of f we have xi minus xj, where I is strictly less than j always. So 1 2 1 3 2 3, right? 1 2 1 3 2 3. In f you never have a bigger index minus a smaller index. F is defined to be x I minus xj, where I is strictly less than j. But once you do sigma star f, that will no longer be the case. Sometimes you have a bigger index minus smaller index, x2 minus x1. Because if I is less than j, certainly it's not true that sigma I is less than sigma j. That's not the case. But however, that is just a negative of, if you have a bigger index minus smaller index, then that's negative of smaller index minus bigger index, which appears in f. So f is a product of some terms. Sigma star f will be product of same number of terms. But some of these terms, it will be the same terms with possibly negative sign. So if you now accumulate all these negative signs, you might either have plus or minus, as this example shows. You have 3 negative signs giving you minus f when sigma was 1 3. When sigma tau was 1 2 3, you have only 2 negative signs, so that give you f. So sigma star f must be either f or minus f. The same terms are preserved up to a change of sign. So sigma star is either f or minus f. Let me say this is my proof. I won't go into a more formal proof, but I hope this is clear enough for you. So sigma star f is f or minus f. Next I want to do, if sigma and tau are in Sn, what is sigma tau star f? This is my next question. Sigma tau is another permutation, right? So I can apply star of it. How is it related to sigma f, sigma star f and tau star f? Okay, I want to understand how is it related to this. So again, I will explain this by the example that we did. So take n equal to 3 and sigma was 1, let's say sigma was 1 3 and tau was 1 2 3. So what is sigma tau? So sigma tau, we are now okay, we are all become comfortable hopefully with products of permutations, cycle products. So here sigma tau will be 1 goes to 2 and 2 is not 2 is fixed by sigma, so that's 1 goes to 2, 2 goes to 3, 3 goes to 1, so that's 1 2. So you close 2 goes to 3, 3 goes to 1, so 1 2 is a cycle, 3 goes to 1, 1 goes to 3. So sigma tau is 1 2. And what is 1 sigma tau star f? If you now do the calculation that we have done earlier, it is x. So f was, remember, I'll write it again here for convenience. F was x1 minus x2, x1 minus x3, x2 minus x3. So sigma tau star f will be, I will just directly write x1 goes to 2 in this, so x2 and 2 goes to 1, so that's x1 minus x2 minus x1. 1 goes to 2, so x2 minus, and 3 is fixed, so that's x2 minus x3, and x2 goes to 1, so that's, and 3 is fixed, so that's x1 minus x3, right? I just look at the subscripts, which are the indices of these variables, and see where they go under sigma tau. So 1 goes to 2 and 2 goes to 1. So the first one changes sign. The second one, 1 goes to 2, 3 goes to 3. So 2 x2 minus x3. This does not change sign. No change of sign. Here x2 goes to 1 and 3 goes to 3. So here also no change in sign. Right? And in the first one, change in sign. Okay, now what is this? This is f, minus f, right? Because there is one change of sign, so it is minus of x1 minus x2, the other two are fixed, so this is minus f. So sigma tau whole star, so this is sigma tau, first you multiply and then take star. On the other hand, what is tau star f? Tau star f was, remember, we wrote that here, it is minus f, but it is x2 minus, so it is f, but let me write down what we got. Okay, so it is x2 minus x3, x2 minus x1, x3 minus x1. Right, x3 minus x1. Okay, so now let's apply, so we have this, let's apply sigma star to both sides. So sigma star of tau star f. What is this? See, when I apply sigma star, I simply change the subscripts by sigma. So, and sigma was 1 3, right? So x2 minus x3, 2 is fixed under sigma, so it is x2 and 3 goes to 1, so this is x2 minus x1. x2 minus x1, so 2 goes to 2 and 1 goes to 3, so this is x2 minus x3. 3 goes to 1 and 1 goes to 3, So you have x1 minus x3. And if you now compare this with sigma tau whole star f, okay, so let's compare them both. We have x2 minus x1, x2 minus x1, x2 minus x3, x2 minus x3. So this term is common, this term is common, and we have x1 minus x3 and x1 minus x3. So we see that, so they are equal, they are same, right? So sigma, so what we have is sigma tau whole star f is applying sigma star to tau star f. So you start with f, first apply tau star, then apply sigma star to it. So this is what we have in this example, and I will now say this holds in general. Okay, so let me quickly say this. So in general we have, and why is this? What is the reason? And the calculation is the following. So what is sigma tau whole star f, which is by definition, remember we take x and we apply sigma tau of I minus x sigma tau of j. Remember again, when I, for a permutation sigma, I defined sigma star f. How did we define this? Let's go back to the definition of sigma star. I start with f and each subscript I simply change by sigma, right? So I change a subscript by sigma, x sigma I minus x sigma j. Here I am applying it to sigma tau. So I change sigma I by sigma tau, j by sigma tau. But now this is same as, and the product is over this set I less than j, I greater than equal to 1, j less than equal to n. But sigma tau, remember that it is a composition, right? Sigma tau is the composition of sigma and tau. The product in the symmetric group, the binary operation in the symmetric group is the composition of functions. So this would be same as x times tau of I, x sub sigma of tau of I minus x sub sigma of tau of j. I am not doing anything in this step. I am just observing that sigma tau of I is sigma of tau of I. Sigma tau of j is sigma of tau of j. But what is this? This is applying sigma to something. So this is sigma star of product 1 less than equal to I less than j less than equal to n of x tau I minus x tau j, right? Because if I take this and apply sigma star, applying sigma star is by definition applying sigma to each subscript. So I am applying sigma to each subscript, so this is sigma star of this. But what is this? So this is sigma star of this. But what is this? This is exactly tau star of product, the same product xi minus xj, right? Because originally you had xi minus xj, you apply tau star to it and then you get this. But this, what is this? This is just f. So this is sigma star of tau star of f. Remember, this is exactly what I have claimed here. Sigma tau whole star f is sigma star of tau star f. Okay, so I don't need this interior parenthesis, so just me write. Okay, so in general I have this.